The purpose of this assignment was to observe the airflow patterns over certain areas of a passenger vehicle and then interpret the observed behavior to make useful conclusions of the aerodynamics of the vehicle, as well as potentially why the vehicle has a certain body shape and why certain engineering decisions were made. The vehicle used for testing was a Volkswagen Up, which has a coefficient of drag of 0.31 and a frontal cross-sectional area of 2.45 square meters. The areas that needed to be investigated on one side at the front of the vehicle are the A-pillar, side view mirror, and parts of the front windshield. In the interior of the vehicle, the airflow through the air vents needs to be investigated. And lastly, at the rear of the vehicle, the flow over the rear window needs to be investigated as well. These areas can be encircled in red in the photos to the right. These softs were then applied to the vehicle in an almost grid-like fashion in the required areas, which at the front of the car includes the A-pillar, the side view mirror, and part of the front windshield. In the interior of the vehicle, tofts were applied in front of the left and right air vents. At the rear of the vehicle, the tofts were applied in the middle of the spoiler as well as on the trailing edge to visualize the flow separation at the edge. Recordings were made of the front and rear of the vehicle from inside and from outside of the vehicle, using the rear window and the vehicle's panoramic sunroof. Observations were made at 4 different speeds, namely 40, 60, 80, and 100 km per hour, as well as 2 videos that were taken for variation of vehicle speed ranging from 0 to 100 km per hour. Both were taken of the frontal area of the vehicle, one from the inside and one from the outside. This gave a total of 18 video recordings that were analyzed to obtain an idea of the airflow pattern over the vehicle.
The airflow patterns look very similar at each of the 4 vehicle speeds. The movements of the wool tufts and the differences in flow regimes just get amplified as the speed increases. This can be seen comparing the videos taken at the different speeds back to back, as seen by the different slides shown here. The discussion will be focused at the 100 km per hour video recordings because the effects are the most discernible at this speed. The near constant direction of the tufts on the windshield indicates that the flow is attached over the windshield. Where the tufts are placed closer to the center line of the windshield, in the direction of airflow, the air moves perfectly parallel over the windshield, relative to the direction the vehicle is traveling in. Closer to the edge of the windshield, the airflow starts moving laterally as well as parallel to the vehicle's motion over the windshield. This is due to the curved shape of the windshield. As the flow moves over the A-pillar, the airflow separates at the sharply defined lines on the A-pillar. This can be seen due to the tufts on the A-pillar that are closer to the windshield, not moving very much, and the tufts on the A-pillar furthest away from the windshield, moving radically in different directions. The flow over the front of the side view mirror remains attached to the surface of the mirror until it reaches the trailing edge of the mirror, where the flow starts to separate and become turbulent. This leaves a low pressure area behind the side view mirror. The turbulent flow around the side view mirror also creates a noticeable amount of wind noise that reaches the inside of the cabin. It also affects an area of flow on the door and side panels of the vehicle behind it. The flow between the side view mirror and the body of the vehicle is highly turbulent. This can be seen by the tufts moving in an extremely radical manner, as well as the tufts actually unwinding into individual strands at the tips after driving a while. The flow over the passenger side window follows the direction that the vehicle is traveling in and is relatively attached to the surface of the glass at the bottom of the window. Observing the flow nearer to the top of the window as it gets closer to the A-pillar and the roofline where there is some flow separation happening, the tufts start to move around and change direction more rapidly, while having a general upward trend towards the roofline and A-pillar. This indicates more turbulent flow and that the flow is moving down the side of the vehicle as well as up and over the roofline of the vehicle. Testing of airflow through the air vents were performed at a speed range of 0 to 120 km per hour, which is the maximum allowable speed on a highway in South Africa. Regarding the climate control settings of the vehicle, the electronic fans were turned off, the air conditioner was turned off, the forward-facing air vents were selected, and the cabin air recirculation was turned off. There was no significant airflow observed through the air vents, even at the maximum vehicle speed of 120 km per hour. This is because the vehicle has a climate control system with air filters and a more complex ducting system than some older vehicles, where the airflow through the air vents is significantly affected by vehicle speed. Again, the airflow patterns look very similar at each of the 4 vehicle speeds, with the recording at 40 km per hour being the only one looking a bit different than the others, because there is not as much motion of the tufts at that speed. But as the vehicle speed increases, the flow patterns and areas of turbulent and detached flow becomes discernible. The discussions will again be focused on the 100 km per hour video recordings, because the effects are the most noticeable at this speed. On top of the rear spoiler, the air coming over the roof is still attached to the surface and only separates as it reaches the trailing edge of the rear spoiler. This is seen through the difference in motion of the tufts placed in the middle of the spoiler surface and the tufts placed on the trailing edge of the spoiler. The tufts placed on the rear window moved in an extremely radical and random manner with no constant pattern, indicative of highly turbulent flow. This creates a large low pressure area over the rear window and back of the vehicle, which sucks in dust and debris thrown up by the wake the vehicle leaves behind as it travels forward. This dust and debris sticks to the rear of the vehicle, including the rear window, and builds up over time, making it hard to see through the rear window. This is an inherent feature of the hatchback shape of the vehicle and why the vehicle is equipped with a rear windscreen wiper. In conclusion, the flow over the windscreen is largely attached until separation occurs at the A-pillar, where sharply defined edges were created by the manufacturers to create a constant location of flow separation, to make the vehicle more predictable in high-speed turns and when experiencing side winds. Majority of the turbulence at the front is created at the rear view side mirror due to its shape and location. The intensity of separation and turbulence increases with vehicle speed, and thus the wind noise also increases. The climate control system of the vehicle has air filters and a complex ducting system that prevents large volumes of air flowing through the air vents while driving at higher speeds. Thus, no airflow through the air vents were observed during testing. The vehicle leaves a large, low-pressure turbulent area in its wake as it travels forward, which kicks up and sucks in dust and debris from the road surface, which accumulates on the rear window of the vehicle over time, and hence why it is equipped with a rear windscreen wiper.